In this video, we're going to do some examples solving least squares problems. So recall that in the previous video, we showed that x hat is a least squares solution to the system a times x equals b, if and only if a transpose times a times x hat equals a transpose times b. So this equation right here was called the normal equations. So we will need to solve this equation with this transpose in it for x hat to get our least square solution. Okay, so I want to make one quick remark before we do an example. So if our equation ax equals b was consistent, then x hat would just end up being the general solution to ax equals b. So usually in that scenario, we wouldn't be finding a least square solution, we would just be finding the solution. Alright, so now let's do an example. Let's find the least square solution to ax equals b for the following. So we're given this matrix A and this vector b. So it turns out in this problem that a times x equals b will be inconsistent. It's a good exercise to form the augmented matrix and check to see if it's consistent or not. And if you do, you'll end up seeing that it's not consistent. So we need to solve this least squares problem. So to do that, we're going to form both sides of our normal equations. So I need to first figure out, let's write this in blue actually, what A transpose times A is. So A transpose will be, so the first row becomes the first column, 1, 3. Second row becomes the second column, 8, 2, 6. And then we multiply that by A, which is 1, 3, 2, 6. And then we multiply this out. And if we multiply this out, I'm going to do this kind of quickly because this is just a computation here. We get 5, 15, 15, and 45 after we multiply these out. So now we also need to do A transpose times B. So let's work out what A transpose times B is. A transpose times B is 1, 2, 3, 6. That was the same transpose we had, times now the vector 1, 1. So when we multiply these, this one I'll do a little bit more slowly. We'll get 1 times 1 plus 2 times 1, and that's 3. And the next entry is 3 times 1 plus 6 times 1, and that's 9. So let's continue with this. Okay, so I need a little bit more room, so let's go to the next page. All right, so let me zoom it in a bit. A little bit more, okay. Alright, so we're trying to solve A transpose times A times x hat equals A transpose times B. This is the system we're trying to solve here. Okay, so we know what A transpose times A is. We just figured it out. It was 5, 15, 15, and 45 times x hat equals, we also got A transpose times B. That was 3, 9. So to solve something like this, we'd set up the augmented matrix and we'd row reduce. So the augmented matrix for this would be, let's see, 5, 15, 15, 45, augmented with 3, 9. And now we could do this by row reduction. So we could multiply the first row by -3 and add that to row 2 and insert that into row 2. And doing that, we get the top row stays the same, 5, 15, augmented with 3. But the bottom row actually becomes all 0. Because the second row was actually just a perfect multiple of the first row. Alright, so we got this. And now we're almost there actually. I'm going to keep row reducing this to put the matrix into reduced form. So we need to multiply the first row by 1/5. And insert that into the first row. So doing that, we divide the first row by 5. So we'll get 1, 3, augmented with 3/5, and then 0, 0, 0 for the second row. So at this point, we're ready to write down the equation for our rows. So for the top row, we would get x1, and I'm going to go ahead and move over the 3x2 over to the other side already. So this will be equal to, well, we have the 3/5 there. And we'll have the minus 3x2 once we move the x2 over to the other side. Sorry, let's write that a little bit better. All right, so now we are ready to write down our answer as a vector. So x as a vector, we'll have x1 and x2 as the entries. So x1, we know what it is. It's 3/5 minus 3x2. And x2 is free because there's no pivot in the second column. So any free variable, we leave that as it is when we write our solution in vector form. And now we could split this up into parametric vector form. And we'll get, first, all the constant terms. We have a 3/5 and 0. There's no constant term in the second entry. And then we'll have plus x2 times the vector with the coefficients of x2. And those are -3 and 1. All right. So there are a couple of things that I want to notice about this. So the first is, what we have here, this solution, this is our general least squares solution. Our least square solution, so what x hat should be, looks like this. Any vector of this form is a least square solution. So this problem, we actually have infinitely many. We have infinitely many answers. So that can happen sometimes when we do a least squares problem. Sometimes we can get infinitely many answers. And I'll talk about how we could have recognized at the start of the problem why we're going to have infinitely many answers. But I'll do that in just a minute after I state a theorem. So one other thing that I want to point out is, well, what if I just wanted one particular least square solution? So to get just one particular least squares solution, we could just let the free variable, in this case we have one, but if we had many, we could pick whatever we want for the free variable. So the simplest thing that we could pick is we could just let x2 be 0. And if we let x2 be 0, what we'd get that x hat is, we just have the vector 3/5 for the first entry and 0 for the second entry. So that would be one particular least square solution. And so just to fix my notation from earlier, it would have been better if above this x, if we had written x hat. So this indicates that, oh yeah, we found the least square solution. So I should be writing x hat there. All right. So next I want to make a key observation. So I want to note that our equation ax equals b has a unique least square solution. So notice that didn't happen up here, because here we had infinitely many. So we will have a unique solution, least square solution, if and only if a times x hat equals b hat. Remember, this was what x hat needs to satisfy. A times x hat needs to be the projection vector b hat. So the projection of b onto the column space. This needs to have a unique solution. So the x hat that will be a least square solution to ax equals b is the same x hat that makes a times x hat equal b. So this second equation needs to have a unique solution. Well, when does this system have a unique solution? Well, that's true if and only if the columns of A are linearly independent. So when the columns of A are linearly independent, then we will have a unique least square solution. So I'm going to zoom it out a little bit. The reason we had infinitely many answers up here was because our matrix A in this problem had linearly dependent columns. So when it has linearly dependent columns, then we won't have a unique least square solution. We'll have infinitely many. So that connects to what we're sort of observing here. And next, I want to state another equivalent condition to this. And this last equivalent condition, this is actually a theorem. So there's a theorem that says the columns of a matrix A are linearly independent if and only if A transpose times A is invertible. Is invertible. So that statement is a theorem. So if we look back at this example up here, so A transpose A, we had figured that out. That was this matrix. This, we might notice that the two columns are multiples. I can multiply the first column by 3 to get the second column. So the columns are linearly dependent here. So A transpose A, because that's what this is now A transpose A, this is definitely not invertible. And that's why we didn't have a unique solution. We had infinitely many. So another thing to note is, when we try to find a least square solution, there will always be at least one. So when we try to find a least square solution, there can't be none. And that's by the construction of what we've been doing, how we've tried to find the least square solution. All right, so in the situation when there's a unique least square solution. So in the situation when A transpose A is invertible, in this case, if we look at our normal equations, A transpose A times x hat equals A transpose times B. So if we look at these, this will be true if and only if, and I can now multiply both sides by the inverse of this matrix. And if we do that, we'll get x hat on the left, and on the right we'll get A transpose A inverse, and then times A transpose B. So when A transpose times A is invertible, we can also write down the solution, x hat, the least square solution, by taking the inverse of A transpose times A, and then multiplying that by A transpose times B. But in practice, we usually only use this formula when A transpose times A is small, usually just when it's 2 by 2. All right, so let's look at another example. So this next example, so A is this 3 by 2 matrix now, and B is this vector in R3. So for this question, I'd like to give you all the chance to try this for about 2 to 3 minutes. So at this point, pause the video in 4, 3, 2, 1, pause the video. Pause it for about 3 minutes and try this question. See if you can work out what the least square solution is. All right, so to do this, the first thing that I'll do is I need to compute A transpose times A. So A transpose will be 1, 0, 1, 1, 0, negative 1. Multiply that by A. So A is 1, 1, 0, 0, 1, negative 1. And multiplying these two matrices, I'm going to just do this quickly. We get 2, 1, 1, 2. So if I do, if I do my row column multiplication, that's what we'll get. And then now I need to figure out A transpose times B. So A transpose we already have. This is our matrix, the first one we had written down here. 0, 1, negative 1 in the second row, times the vector B, 1, 2, 3. And this multiplication I'll do quickly as well. This ends up being 3, negative 1. All right. So now what we need to do is we need to set up our normal equations. So A transpose A times x hat equals A transpose times B. We need to set this up. All right, so, well, A transpose A, we had figured out what that is. That was 2, 1, 1, 2. And that needs to multiply the vector x hat that we're looking for to give us A transpose B, but that was the vector 3, negative 1. So we're trying to solve this. And we could write this as an augmented matrix as 2, 1 augmented with 3, and then 1, 2 augmented with negative 1. All right, so I've actually gone ahead and done the row reduction for this already. So I'm going to go ahead and just show the row reduction, because I think that's not too bad from here. And I was accidentally revealing the answers, so I went ahead and erased that. Okay, but it's basically one step from here. So I've gone ahead and done the row reduction because it's not too bad. But at this point, we could just read off the equations, read off these rows to write down our answer. So x hat, our solution, so the first entry is going to be 7/3. That's what x1 equals based off of the first row. And the second entry, based off of the second row, we'll get that x2 is negative 5/3. So negative 5/3. And that is our least square solution right there. So notice that our solution is unique this time. We just got one answer. And it's unique since the columns of the original matrix A are linearly independent in this problem. So if we were to scroll up, here's A, the columns, there's just two columns. So we can check if two columns are independent by seeing if they're multiples or not. And these are definitely not multiples. So these columns are linearly independent, and that's why we ended up with a unique solution. So in the next video, we're going to look at an example of least squares to what's called the line of best fit.